Hello everyone, welcome to First Principle Engineer. Here we are going to discuss and get a deep dive on the different popular books in engineering with hands-on examples and different approaches of doing the same thing at production level. Today we are going to discuss about the famous Inference Engineering book by Philip Kiley. I don't know how to pronounce that Kelly, but it's a good book which I've seen. Today we will have a good deep dive on the prerequisites, that is the chapter one and the introduction of this book. So let's get started. Mostly today we will cover a high level view of what we can expect from this book and what are the things which we need to know before starting the inference engineering. Mainly inference is not always every time required. It comes at a stage when the product has been proved as a good market fit, as inference at initial stage requires a good amount of money and compute. So let's get started. Inference is a valuable category in AI industry. Firstly, let us know the difference or the things which are required to start inference engineering. The main thing is to know which LLM model we are going to use, or whether it is open source model, closed source model, what is the size of the model, and what are the number of requests we may face in a company. So first, closed source models, as we already know, GPT by OpenAI, Claude by Anthropic. These are the famous closed source model. And open source models are like Kimi, Llama, DeepSeek, which comes under MIT license. So we can fine tune them and make them according to our needs. So let's first understand clearly what are the things which we need to keep in mind before starting the inference. Inference is always not the priority, it is always the second phase in the AI model's life cycle. What we can say is, firstly, we need to have a model to use it in the production. It can be a closed source model or an open source. Creating a model requires training and large amount of data. But once we have model, it is important for us to use it in the limited infrastructure and the cost which we have. So inference mainly means serving Gen AI or generative AI models in production. In last decades of ML boom, data scientists and ML engineers had a quite good time in serving plain ML models or neural networks just on a lightweight CPUs. But the today's world has been shifted towards Gen AI after the release of the famous research paper Attention is All You Need in 2017. The architecture itself is so heavy that we need GPU for complex computations and the thinking of the models. So doing inference mostly is requires three layers. We can say them as runtime layer, infrastructure layer, and tooling layer. Runtime, infrastructure, and tooling. Mostly we have these three layers for we should take care of mostly these three layers while inference engineering. Runtime is mostly optimizing the performance of a single model on a single GPU backend instance. Means we need to make our model or LLM in a way that it uses our available GPU efficiently, which we will see in future how we can do that using CUDA kernels and PyTorch library and many different things to optimize the LLM architectures. Like we have seen the migration in LLM models, different LLM models. When GPT-2 was released, it was having 96 layers, most probably at that time. Currently, I don't know because it is not yet released in public. And we see that the DeepSeek model having the same number of weights is cheap and efficient for the regular tasks. It is because they introduced a new architecture in their model, that is a few things like KV cache and MOE. These things were introduced by DeepSeek. So MOE, I think most of the people might be knowing mixture of experts. Uh, we will see these things in detail in future. So these kind of mathematical things, if we are able to change in the model or optimize in the model, we can make sure that the model is efficiently using our GPU and not wasting resources. This comes under the runtime layer, and next is infrastructure layer. Obviously, that how much ever you optimize your model in runtime layer or runtime, if there are more requests to be served for a LLM, single GPU won't be sufficient. That everyone knows. As the request increases, we need to increase our infrastructure. So we come to infrastructure layer. Here it is mainly about having different kind of or having more number of GPUs and serving a single model on more number of GPUs. That comes here in infrastructure layer. We can say that scaling the model on multiple GPUs so that we can maintain a good uptime of the model while serving more number of requests. So here mostly we will discuss how we can split a single model on a GPU cluster which will have multiple GPUs in it, because obviously as we know models nowadays are very big in size. It is impossible to load a complete model in a single GPU. GPU's RAM, as RAM of a single GPU is limited. Even even if you buy a costly GPU, industry level GPU like A100 or H100, even they have limited RAM. If the size of the model is increased, then at that point it is impossible to load the whole model on a single GPU's RAM. I hope everyone knows that how or we will discuss more about this in future. Like whenever we try to request a model, GPU loads all the weights to the RAM from SSD, and once those weights are loaded to the RAM, the mathematical computations happen in the RAM. So we require space or a buffer space to uh, a buffer space to to compute these mathematical operations, which are huge matrix multiplications and different activation functions. So if a model itself is big, then we won't have space to do these. We won't have enough space in the RAM to do these computations on our GPU. One more problem is if the model size exceeds to a very large extent that the GPU doesn't have that much RAM. Then that time we split the GPU's layers and weights to a cluster, or a model's weights to a cluster where there are many GPUs. Like example, if this GPU has X GB of VRAM or virtual RAM, we will discuss about this in future. If a GPU has this much RAM, X GB RAM, but the model itself is YGB and X is smaller than Y, then it's impossible to load the model on this GPU and do computations on it. So at this point, what we will do, we will divide this Y on the number of GPUs we have, let's say N approximately, and whatever we get Z, let's say those many weights we deploy on a single GPU. I'm just giving a high level architecture. You will see in future. Actually, this book takes these things to a practical level. We will do hands-on in future. I'm just giving high level view. So once these are divided on this, we will see how we can inference whenever a request comes, how we will deviate these requests and compute across multiple GPUs and then give the output. That is what we will see. This comes under infrastructure. And next is, we call this tooling. This is mostly for engineers see how the model is performing, what is its reasoning, or we provide them enough tools with a correct level of abstraction so that it is a good balance between control and productivity. They can see using these tools how much each GPU is being used. Like there may be problem arising out of, let's say we have 4 GPUs, there may be a problem only 3 GPUs are working to highest they can work, highest resources they are consuming, but the fourth GPU is empty. The load is not getting diverted to it properly. These kind of things should be visible to engineers so that they can debug and also create a better solutions for using the tools we have so that they can optimize the runtime layer and infrastructure layer efficiently. That kind of tools we should provide. Mainly these 3 layers are there at Inference Engineering. The book also covers many, also gives an example of what runtime and infrastructure layer has. Mostly runtime layer, they they give examples of PyTorch, CUDA. These kind of things are done to optimize the runtime part of the inference. Runtime may we use caching, quantization, or parallelism, doing the computation parallelly on different GPUs. We use PyTorch and CUDA for these purposes. And many things. We will discuss this in future. And infrastructure at infrastructure level, like we have a cluster of GPUs here at infrastructure layer, we will cover routing. Means if a request comes, then how is it routed to different GPUs efficiently so that no GPU is idle or no GPU is getting overwhelmed with its tasks. And load balancing, auto scaling. Auto scaling is like when a GPU is off due to any power cut, power shortage, or due to any hardware default, then how we can on the spot start a new GPU and start routing new requests to it. This is auto scaling. These kind of things, and storage, networking, these kind of things come under infrastructure. Okay, and at runtime level, we see that different model performance techniques we are going to discuss, like batching, caching, quantization, etc. Once we optimize the runtime layer, if it is working to its highest efficiency, then as an engineer, now our task is to optimize the infrastructure, because after the runtime layer is optimized, means that a model is using all the resources of a GPU efficiently, then it's not a problem of CUDA or PyTorch. Then it's a problem of infrastructure. Then we should see different things we can do on infrastructure layer to optimize the overall workload and inference. This is the high level view of what we can expect from this book. And as we know, inference engineering is growing nowadays. Many LLMs are coming, many open source LLMs are also coming up. So companies mostly need people who can optimize their resources in a way that they can rely that the infrastructure can rely on and work efficiently on more number of requests or a sudden spike of requests instead of completely destroying the user experience. Okay, the book also gives the clear example of how we need to choose a right solution for our need. Let's say that a sports teacher comes to a school to select a students for basketball and let's say gymnastics. Then obviously the sports teacher would choose tall people for basketball and short people, or we can say the people with more strength for gymnastics part. It's not that one skill is better or one skill is different. It's about having the correct solution or power with me for my problem. We Every problem has its solution. Instead, means we shouldn't go with a generic solution, or there is no hard and fast rule that one solution is correct and the other is wrong. The solution is completely based on the budget requirements, etc. We will discuss these things like what is the latency budget, unit economics, usage patterns, and which model we will deploy. Every model has their own architecture. Every model consumes different amount of GPU. So one solution for one problem and the other solution for other problem is completely fine. There is no correct or wrong solution here. Mostly inference way we can actually, there are two ways that you can add AI models to your product in the company. They are like shared inference or dedicated deploy. Shared inference is like you have a single API key like we generally have now for OpenAI and Anthropic uh, and Open Router. Many of these have directly the APIs, which we can directly call them and use them for our requirement. This is what is shared inference. And one is dedicated deployment. We can buy a GPU or rent a GPU and then install our model on that GPU and let the request comes to our GPU. Both of them have their own pros and cons. No approach is correct or wrong, as I said earlier. It completely depends on requirement. Let's say what are the pros of shared inference and cons of shared inference. On shared inference, directly you create a OpenAI API key and hit their API with a key to get the output. On this shared inference part, we have to just pay for the amount of tokens we are consuming. Whenever we hit an OpenAI API, we will consume some amount of input tokens and some amount of output tokens. We will pay just for this, how much we are consuming, input and output tokens. Also, there is no cold start times, means that model is always available. There is no restart or those, or we shouldn't care as engineer whether the model is up or down or working or not working. We are just paying for the key and we are using that model. So minimal engineering work is required. You just need an API key. I will show you how you can do that using Open Router example. ROUT. Open Router. You can come to Open Router, create API keys. We can sign in with Google or sign in with GitLab or GitHub, anything, whatever the things they provide us. Once we are signed up, 1 second. Okay, next. Continue. Okay, This is the open router interface. This is actually a place where you can get different models at a very low cost. Even the open source models are hosted here, which you want, if you want, you can use instead of hosting them on your own infrastructure. This is a good thing. API keys, we can create any API key like this by doing new key, etc. By putting this information, you can create a new key. Once that new key is created, you can hit their API and use the models. I hope you can see the models here. Yeah, different models are there like Gwen and Claude, and Opus 5 is also hosted. A bit of models are free and many models are paid also, but they are at a very low cost. See, many NVIDIA and Nemotron, many models are also freely available here. You guys can try it. Embedding models are also available, text models, image models, different kind of models are there at a very low cost. As you can see, this 32,000 tokens context it has, and the cost is 0.6 billion per pixel. Okay, this is 32,000 pixels per context. Okay, totally 17.6 million tokens at a very low cost. These models are. This is what comes under shared inference. You can just get a API key and use it. But there are also cons of this approach. The cons are like cost scales linearly with usage. Whenever you hit the API, you consume the token, the cost increases accordingly. Whenever the usage increases, the cost increases parallelly. Next, also it is like, for example, whenever you use this API, let's say they had some issue from their side, or they had many people due to some reason, or their infrastructure got collapsed, or due to some issue. At that point, it is your product that will face downtime because of dependency on them, and we cannot control the latency or model quality or rate limits, as we are just using them. We don't have any low level control of what is the speed of the inference and those things. These are the cons of shared inference, and the opposite is with the what is it? The opposite is with dedicated deployments. There we have our own GPU. We can we can from our end try eh, to control the latency, to increase the rate limits or to decrease the rate limits according to the usage. And also, but there is one, on the dedicated deployments, we also face a issue like we are the owner of the GPU at that time. So even before starting, or if our product is new, before knowing the market fit, we directly buy a GPU to try our product. This will cost a lot of money. If we at the start itself, if we put a lot of money on GPUs, then it is very difficult for a product to know, or we won't have that much budget at initial stage to buy a complete GPU. So at that time, shared inference is good. But when the product is market fit and it has reached a stage that we need a control over latency and model hostings, and we don't want the cost to increase linearly because of tokens, that time we can go with dedicated deployment. So both the approaches have their pros and cons. It completely depends on what is our requirement. Like mostly what we see is the inference engineering mostly comes in when you have a foundational model. You means you have trained your own model or fine-tuned a open source model, and you want to host it, like generally OpenAI and those things are doing. Those companies are doing this thing. They are creating their models and exposing them as a public shared inference. That is called foundational models. And the inference problem is when you are just building a inference platform where the people can host their model. like Grok, you can say GRO. This is one inference platform. They allow to host different models here, and they have their own architecture, which which allows people to host their model here and get uh, faster output because of their architecture. Now once sometime later we will discuss this architecture is not covered in the book, but it is very interesting and a good architecture at a hardware level that they have done. If you guys are interested, please comment. We will plan a lecture on this also. They have their own hardware. Here we can host and get a better output. Give it a try. Some models are also available for testing and free. So give it a try if you are interested. This is what is an inference company. They don't have their own AI model, but they use a architecture called LPU, language processing unit, which allows them to to inference a model or get a more output from a model at a very high speed. Let's in future let's plan a session if required for this. Okay, so that is one part where the inference engineers mostly try to build the things at a very low level. One is foundational models, which are like OpenAI, Anthropic, and Google and different companies, and one is like infrastructure company like Grok. Okay, but as a developers like we, or as a solo developer or a startup founder, we we generally don't create our own inference platform or something because that is a costly part. Mostly we software developers or engineers play around things like we are making our mostly like wrapper applications like code editors, which will have some AI suggestions and some chatbots or some summarization tools. So yeah, these are like AI native applications. Or also we can say that these AI native applications which we generally build day to day are what we can say is they have different considerations we should keep in mind before building. For example, if we are building some agentic platform, like what we can say, N10 workflow we are making, or some agent we are making that can read your emails and reply to them automatically. These are the agentic tasks or agentic applications. So for these kind of applications, if we as a developer should consider things like one API call for my or agentic architecture. One API call to agentic architecture does many API call to the LLM. Let's say example, this is LLM which we are using. It can be anything, GPT or any open source or closed source LLM as we discussed. And this is our application which is agentic, or we can say that it performs or it automates a few tasks like reading email. Whenever you hit a request to this, our application, okay, okay, whenever you hit this application, our the code or the logic we wrote here is like whatever we share the context. Let's say it is a email replying bot or agent. Whatever the context we share it got the email context. It hit the LLM with our some system prompt hard coded in this application. It hit the LLM. LLM gave some response. Yeah, let's say it hit the LLM for a reasoning part to know what kind of email is this. It got some response. Then we wrote the logic that if this is a promotional or sponsored email or advertisement email, then delete this. Once it got that information of what category email belongs to, it will again, according to our logic, it will again hit LLM to perform next task, and this loop goes on till the task is completed. So a single task which we gave it to do to our application that made some NLLM calls. So this kind of things we should keep in our consideration, that one call to agent doesn't mean one call to LLM. It can be many calls. And if you are making a simple chat interface, like performing just a RAG, uh, retrieval augmented generation, hopefully we may have a lecture on this in future, or there are many YouTube videos which you can see to know about RAG. And this is a very easy thing to understand according to me. So let's say we made some customer support chatbot which does a RAG on existing documents and replies to user queries. This is like single API call. We have a bunch of documents, some cosine similarity or similarity search happened at our DB side, and we got a bunch of documents. Those bunch of documents we gave to LLM along with the user query, and then LLM gives the response which we show to the user. This is like a simple chat. So here the considerations which we may make is, what is the time taken by our infrastructure to perform this pipeline and give user the output. Mostly we have a few metrics to see, or to judge the speed of LLM, like uh, TTFT, time to first token, and TPS, which is token per second. We will discuss in this video only in future in depth about these metrics which we need to keep in mind. And there are more examples discussed in the book which we need to keep in mind while building these applications. Like we discussed, agentic application, plain chatbot, and if we are making voice application, then the voice application in the sense real time translation between languages, those kind of things. Then at that point we should consider the end to end latency of them is communicating with you like a human. That time the speed matters. It can't be like I'm converting whole thing to text and making it understand and big pipeline is happening, which may destroy the user experience. So the end-to-end latency for a natural conversation, that kind of things are required to be considered beforehand. And if you are making a media application where that is a virtual try-on for clothes, jewelry, and those kind of things, at that point, the correct balance between the output quality and speed matters. If you are just giving speed and the output quality is third class, then your application won't be a good product fit or market fit. So there are a few examples which you can read on your own. I gave a few. This was one part of the considerations we need to have of our app, AI native applications. The second thing we should think about before building these AI applications is online versus offline. What it means is, so the example which I can think currently is in offline versus offline. In online versus offline is online in the sense a request comes in and you process it and give output. But at this point, we want the latency to be low. These kind the example the like we say code editors. These comes under these kind of applications where we want instant processing. The based on the user speed of typing, we can't be slow that the person have typed everything and then we are giving a suggestion. That time we want the latency to be as low as possible, and so that the user experience is good enough. And the offline compute means that background processing by LLM. The example is like embedding creation or translation tasks. Like I gave a huge what I can say is a huge bunch of data to the LLM to create embedding or to translate it. Then as an end user, it doesn't matter to me that if it takes more time. I just care that I want the correct output. Here, the throughput matters more. So, based on our application, it is in our hands to decide to what kind of trade-offs or what kind of pros and cons our application would have to give a better user experience. Like the examples I gave, if a code editor has a very high latency, then it completely destroys the user experience. So, and in the offline compute part, it is it is like I should deliver a better quality. It doesn't matter if it takes time. Like in future, we will see how a single LLM we will use for both of these tasks. Example is like if we have a whisper model, okay, which is a speech to text model. Okay, this is a speech to text model. We will see in future how this single LLM we will use for our both offline part and online part. Example is like the examples I gave currently, generating or suggesting the code snippets, creating embeddings, or digesting the whole huge corpus of data inside. We will use the single LLM and create infrastructure around it based on our use case. This is where inference engineering or infrastructure, this kind of layers come into the picture. Next thing, before creating AI native applications, to keep in mind is whether we are creating our product for B2B market or B2C market. Like our product will be going to be consumer facing or business facing. Because if it is consumer facing, then we need to create our application in a way that it allows or it has enough compute so that if many requests comes in, then we should be able to handle it. Also, the consumer may do any kind of tasks, so we must have a better guardrail layer also for a consumer based application. Not only consumer based application, the guardrails depends or varies from consumer to business or B2B application. As if for example, if we are creating a like the previous example, if we are creating the LLM application which replies to the email automatically, then if we are making it consumer facing, then we should keep enough amount of rate limiting, so that if a consumer is continuously hitting that, because if the consumer is completely hitting that API or our application, that may harm our infrastructure. So that point we should keep in mind these kind of things. And when you are creating a business application or B2B application, at that point we have to keep in mind the performance and reliability for the application. For example, if you are creating a chatbot for a business, then it should answer the user correctly, means it shouldn't hallucinate or give the wrong data about the business to the user. Like there was a famous incident recently. McDonald's had a chatbot which which wrote Python or normal code for the user requirement. This was maybe because of no proper guardrails, so it never restricted the user from generating the code. Instead of people instead of using that product to know about McDonald's, people started to use it as a code generator. So these kind of things we should keep in mind before creating applications for different use cases. And also cost in a B2B, if we are creating an application in B2B segment, then mostly the margins are high as business pays you more money compared to a end consumer. So in both the cases, you should keep the cost also in mind before creating an infrastructure or application, which there is a benefit to the business. or your application where you can save money or make money. Also data sovereignty and privacy, different kind of things you should keep in mind before creating these two different applications. Like I gave the MACD example. If uh, if these kind of guardrails are not kept, then the business may incur loss because of these things. I think it was a very famous news of McDonald's chat about. Yeah, see, it's a very famous news. Are you okay? These kind of issues are always there. See this McDonald's AI bot answers Python question. These okay. You see, if not, let's proceed further. Now, next part before creating your application is these are the things which we have discussed to keep in mind before creating your application. Now, at a lowest level, these applications are built around an LLM. So the next and most important part which comes into the picture is which LLM would you use for your application. Everything is important: hardware, infrastructure, runtime, optimizations, architectures, smaller model or bigger model, everything. But model selection is the most important part. The good example that I can give you currently is, let's say, in a company, if you are having a chatbot or a bot which understands the plain English and converts into a SQL query. Okay, SQL query. This is the LLM which we have. Now, as an engineer, it's it's in your hands to choose a good LLM for this task. Now, there are two options or a few options I can say is like either you use a closed source LLM like GPT or OpenAI. Okay. Okay. But as we know, SQL is a very what we say compact or fixed language. It doesn't have many variations. For example, select star would remain select star whatever the user says in. Okay. So we don't want a LLM which reasons a lot or which is a very big LLM with a more number of weights. We don't want that kind of LLM because our task is a very small task here, generating SQL query from English. So if we use this OpenAI or any big model, it is just like killing an ant using a hammer, which is not worth it. You are just wasting money. The next option is having a small model. Let's say it as Kimi or DeepSeek or any small model which you can think, or GPT-2, the older or the old variant of OpenAI, ChatGPT. If you have that kind of small model, even we can give it the English input and expect the SQL output, because to generate this from English, it doesn't require much reasoning or much thinking out of the box ability. Here we can save money because of or we can say that we can save money on tokens and compute, etc. The other thing is, if these kind of small models are not performing accurately for this small task, which may happen as they are old or they don't have enough reasoning because we have small model, here then we can fine tune this model on a data set which has input as English and output as MySQL query. Then if you fine tune this, it is just one time cost. After that, the cost is literally nothing. I can't say nothing, a very small task. So at the end you would save a lot of money by using this instead of using big models. So as an engineer, it is our task to choose a better LLM for a task which we have on our hand currently. And for a bigger task, like if we want to make an agentic application, then we want a good amount of reasoning. Then we can use big models and pay enough money for these things. So as an engineer, the model selection is in our hands, and we should choose a model that saves cost as well as delivers our task at a very high quality. In simple mathematics would be minimize the cost, maximize the quality. Okay. And that is this. So as I said earlier, one solution is not always the correct solution. This solution we can't use for agentic applications, and this solution we shouldn't use for small tasks. Both of the solutions are correct, but with their own requirements, and both pros and cons. Next, after the model is selected, we have chosen the domain, and we have considered different things like what kind of guardrails and what kind of input, output, and latency for our application. Next part would be evaluation. This is the most important part. Once you have LLM ready, your application is ready around it. The next part is to evaluate how the things are working when you give the input and get the output. You should evaluate the time taken and the quality of output which it is generating. And I think this is the part which we should focus first, or invest our time first on this instead of investing time on making the model fast. Because if we just invest our time in making the model fast, then but the quality of the model is not good, then it is just like creating a good thing which is useless for our purpose. So first we should optimize the quality of the model output of the model, then try to speed it up using different things like caching or or less token consumption or some those kind of things which we will discuss in future. There are different benchmarks for models also, as we know, MMLU and SWE benchmark. I'll show you that also. Okay, view benchmark. It is it is massive multitask language understanding. You can read about this. And one is SWE benchmark. There are many benchmarks, but also there is a saying that when you have a benchmark like we currently have, or a fixed output on which we are testing a model, or we are preparing our model to give this output at a very good or a very good output for this benchmark, then there is a Goodhart's law that states that when a measure becomes a target, it ceases to be a good measure. Means if you test, or you make your model to just give output on this, or a good output for this benchmark, then the model would just learn a pattern, or it would just learn a pattern to just give the output so that it passes the benchmark. It would then it would just lose its capability of thinking outside the box of this box. So for evaluating a model, it is always, or I can say that there is a good, you can check whether the model is useful, or model evaluation is useful. You can check that by first seeing your data. You can see what kind of request comes in, what is the most difficult problem that your LLM may encounter. Once you identify that, you can test the LLM on this difficult problem that it may encounter in future. If it is working good on this, then most probably it may work good on other easy problems also. And always use existing tools for evaluating your models or evaluating your AI application. It is because if you try to create your own infrastructure or everything from scratch, it may take time. There are many available tools or cases, or we can say examples and libraries, frameworks for creating these eval suites. Now, once we have decided or we have thought about the things which our application may encounter, the things which we should keep in our mind before creating application, or knowing the requirements of the application, and then choosing a LLM wisely. Next task and create and then evaluating the output of the LLM. Next part is to fine tune a model to domain specific quality. I would say this, that fine tuning is not always important or it is not always necessary. You should go with fine tuning only when you want your application to be what we say to change the thinking or the what we say the behavior of the model. When you want to change the behavior of a model and it's a business requirement, then it is good to fine tune a model. Fine tuning is mostly just changing the, let's say, these are the weights of a LLM which we currently have. We would fine tune means we would change these weights to give a output in such a way that in a way that I want, in a desired output, in a way which I want the output. So I would change these weights not much. I would make it as D, B, and C. This is a very small example which I gave. So we were fine tuning simply means that changing a few weights or model weights to get the desired output which we want. Okay. As I said, this is not always mandatory. It depends on the data you have. It depends on the use case you have. It depends on the eval suits you have made. These kind of things. Like I gave the previous example, we can use fine tuning to create a English to MySQL converting model. That kind of things, when you want a small model to behave like a big model because it is a small or easy task, then we can go with fine tuning, and it depends on the data we have currently. Next, yeah, fine tuning is also a heavy process, as you guys know. It requires a good amount of GPU and compute, and also a good amount of data, domain specific data to which we want our model to be adjusted. So there are a few mechanisms which we will discuss in future, like LoRa, LORA, low rank adaptation, and QLoRa, quantized low rank adaptation. These kind of things are there to fine tune a model in a cost efficient way. These things we'll discuss in future and also do a hands on here. And also we have now distillation is one way of fine tuning a model. Distillation means I have a bigger model. Let's say it is llama 70 billion. Okay. And I have a small model. Let's say it is Quen 3.5 something, small model, any small model. Now I want this model to reason according to the bigger model. This case comes when you have a limited amount of infrastructure, less amount of GPUs to host your model on. You can afford only a less amount of RAM. That time it is better to download a smaller model, but we want the reasoning of this model to be equivalent to this bigger model. That time we use distillation, or we call this method also as teacher and student model, where the bigger model acts as a teacher and smaller model acts as a student. We will see this in future. We will do hands-on also. We will try to what we say distill or create or at least use a distilled model. Like you see many big companies like Facebook also, it releases different versions of models. Like we see Llama 70 billion and Llama Distill, Distill Bird we see. Distill means the same thing here, that this distill model have been taught or it have less weights but have been trained on the by the outputs from a bigger model. Here what we generally do is whatever is the from output, that doesn't mean the final text output which we see. Here I mean the logits. We will discuss, don't worry, I'm just giving a high level view. The logits is the what we say array, or we can say a vector of different probabilities. Let's say this is the probability that next word in the current sentence should be some a word, a. This is probability of that. B, this is the probability of next word. This is probability of this. Then what LLM does, it selects the maximum probability and says that this word or the word at index 0, 1, 2, 3, or at the index 3, word at the index 3 has the highest probability, means the third index word is the next word in the current sequence. So instead of giving this final text output, we give this vector or this logics to the student model, so that student can learn the things like predicting the word or predicting the probabilities of different words instead of just predicting the next word. Okay, but this also has a catch, like generally which we saw that in January 2025 something, DeepSeek R1, the famous or the flagship reasoning model of DeepSeek R1, they it was a very big model. It was having approximately 671 billion parameters at that time in DeepSeek R1. Then they released a smaller models or distilled models at that time on Llama 3 and Qwen 2.5. These models were released by them. These models had a similar behavior or reasoning behavior as same as DeepSeek R1, but they failed on intelligent benchmarks or intelligence benchmarks, as the small model learned only the things which the things like what we say the probability prediction of the words, but it never learned the reasoning or the pipeline in which the teacher model is producing these probabilities. Obviously, this is not possible because the bigger model has more weights, so it has different flow of numbers from one layer to another, and smaller model have less number of weights, so it cannot or it can't simulate the same kind of flow of numbers from one layer to another. It somehow learned the probabilities or logics from the teacher model, but it never learned the reasoning behind or the number flow. This is one catch in the distillation process. Also, one more problem here is that if a teacher model predicts or what we say or give a wrong output confidently, then even the student model also learns that wrong behavior or a wrong output in a very confident way. So if the larger model is giving wrong output, then student model will also give the wrong output. These kind of things are there. Next, let's proceed further. Once we have seen a different things before creating an AI native application for different use cases which we may think and which we will dig deep in future. Next thing is measuring when we have a complete thing ready now, the architecture LLM, and we can say this is a complete our application is ready. The next point comes is measuring the latency and throughput so that we can provide the user a good what we say a good output or good user experience. This is where measuring latency and throughput comes into the picture. Generally, in software development, we measure throughput and latency of the API based on the time difference between the request sent and the response received. Okay, but in LLMs, that is not the case, because LLMs we generally stream the output from LLM. Okay, pardon my handwriting. STREAM. Okay, we generally stream the output. Like we won't wait for the LLM to generate a complete text, because obviously it may take more time and user won't like that. So what we do, as the LLM generates the next word, we show it to the user. I think you have seen ChatGPT and different. Let's say, let me try. I'm logged into ChatGPT. Okay, like see, if I say hi, it won't give me the complete text. It would stream like this: Hi, how can I help you today? In that way. What can you do for me? It would stream. It would give one text at a time. It won't give a complete text to me. It would give me one text at a time. This is called streaming. We would generally, I would try to show you on the API level also. Just a second. Okay. More. Yeah. Payload. Yeah. See this event stream. We are sending the complete stream of the words the LLM is generating. Okay. You guys can also see this. Mm, See different things it streams instead of directly giving me the complete text output. Okay. So in LLMs, we can't judge based on the request, based on the difference of time between request and response received, as we are streaming. So we have different metrics, which we discussed in this video at the start of the video. Maybe I told you about TTFT, like time to first token, which is when you send a request to LLM, or we can, or our application, that time whenever I see the first token on my screen, that is, I'll show you, or a first word, let's consider word for now. Token, will see what this token means, you'll see in future. Okay. When I asked it, what can you do for me? It said me this answer. So the time between the request sent, the difference of time between I received quite, and that at the time when I sent this request, the time between the response quite and time to first token. That is called as time to first token. With streaming output, how long does it take for a user to see the first output token? Lower the TFT, lower the TTFT, the better is the latency. This is one metric, and the other, and one more metric is TPS. That is called as token per second. Yeah, TPS and TTFT. Okay, TTFT, time to first token, and this is token per second. How many tokens, or how many tokens each second does the user receive after the first token is generated? This is called as TPS. Example here, after the quite is received to me, then within a second, how much amount of text I am able to see, or how many tokens I am able to see within a second, is called as token per second. But but like token per second is a very generic metric. So we have a specialized versions of TPS like PTPS, which means perceived TPS. P E R C E I V E T, perceived TPS. Perceived TPS means tokens per second on UI. I would try to explain it. The observed tokens per second per user that the after the first token, the number with, like we said, the generalized what we say generalized TPS is only perceived TPS on for one user. The token speed which comes on the UI, it is not. I will try to explain in a better way. Let's see. We have an LLM and we have our we have LLM. This is LLM and we have our application. I got a request. The request goes through our application, had some pre-processing, and then that goes to LLM. Okay, and then again comes to application. A few pipelines are executed, and the output is received. Okay, so the difference between the difference in time between this and this is called as perceived TPS. Perceived because how much the end user, how much speed the end user noticed is called PTPS or perceived TPS. Next is TTPS, total tokens per second. Okay, TOTAL. Okay, perceived tokens per second. Here, what does it mean? The GPU speed to generate tokens per second. That is, I got the request, application process that request and sent it to LLM. Then LLM generated tokens and it gone through a few pipelines and went to user. So the the time difference between the LLM generating first token, this LLM generating number of tokens per second is called as total TPS or total tokens per second. It because what we say, the application latency or the application processing time is not included here. Only the GPUs or LLM time is included here. That is total TPS. The GPU speed, the speed of GPU to generate tokens per second. It is also called as throughput. So latency is the time which user saw or user noticed, and throughput or the TTPS is the time which our application or our application took or not application took or the time the GPU took to generate the first token. You can also say it as the total time user saw minus the time required for the pre-processing and post-processing of the LLM response is the total tokens per second, TTPS. Okay. The next version of TTPS is inter-token latency or ITL, inter-token latency. Okay. ITL, inter-token latency. This is the time between each token per second. Means, let's say a token is generated. First token is generated. Then after some time, the second token is generated. The time between these two tokens generation is called as ITL, inter token latency. The latency between two tokens, we can say. Okay. These are the few metrics to measure our latency and throughput. As these kind of metrics will help us in optimizing our application further. If I know how much I can, by these metrics I can know where the application is consuming the most time. It is consuming at the GPU end or application end. If we know this, we can optimize that specific thing and increase the total or make the end user experience better. Also, there is one catch. I won't take much time on this. There is one catch on latency, which we see in general software development also, irrespective of AI, which I would like to highlight in this at this stage. is, for example, you have 10. This is not LLM. I will say again, it is not LLM based or LLM dependent thing. It is a general software problem, software industry problem. Let's say you have 10 requests on your server, and it can be any server, backend server or LLM server or anything. It can do anything. Okay. If you have 10 requests on your server, now you want to know how much time the or how much time your application is taking to deliver the output. It can be tokens or any response to the API or anything. How much time it is taking to give the response to the user. Okay, what you would do? You would see that these 10 requests I have. I would check time taken for each request. Let's say each request takes 1 second. Okay, okay, but a catch. Example. Uh, uh, okay, let me rephrase it. Let's say one request takes 1 second to give the output. So the average time is 1 into 10 because there are 10 requests. Okay, and I will take average of this. So divided by 10 because we have 10 requests. So the average time would be 1 second, correct? We can see that average time is 1 second. But now let's say 9 requests among these 10 requests are taking 1 second, and the last request, the 10th request, is taking uh, 10 seconds due to some server issue or the high load on it. Okay, again we would take average 1 into 9 because 1 second to 9 requests plus 10 because because one request is taking 10 seconds, last request is taking 10 seconds, average, right? Divide by 10 because you have total 10 requests. So this will be 9 plus 10 divided by 10, which is 1.9 on average, correct? So according to me, or as a engineer, according to me, the average time taken for 1 second for one request is 1.9 seconds. But is it true? But is it true? Because as we can see, 9 people are getting the response in 1 second, and the one person is getting response in 10 seconds. According to that person, the application is third class, and he is because of the speed, he won't use our application. We lost one customer here. Okay, but we won't know that because we are seeing the average. Average is 1.9 second. I would think that my application is performing very good. 1.9 seconds is average for per request. So according to me, my application is very good. But is it? No, because one request out of 10, or we can say that we are losing one customer on out of 10 customers. So this is not a good performance metric, or the not a good latency measuring metric. Here what we could do in a better way was take the 10 requests and plot them on a graph or some place so that we can see. Let's say first request takes 1 second, other request takes 10 seconds. Like that, 9 requests I would plot here, and the 10th request takes 10 seconds. Okay. If you plot like this, my requests, different amount of requests, like let's say I have 100 requests, and I have plotted different the time on the time they take. I have plotted them, and if I don't know if you have heard, or you can know more about this. There is a thing called P90 or P95 metric, which simply means percentile. The percentile is same like which we have in JE. If I see at this point, let's say this is some nth request, okay, then It means, what it means here is that P90 means, let's say P90 is 2 seconds. Here this means that my 90% of the 90% of the requests are getting served in 2 seconds, and rest of them are getting served in 2 seconds. Okay. Here we can clearly see that how many requests are getting served and how many requests are not getting served. Let's say if I see P95, then which means that 95, what we say, if I have 100 requests, then my 95 requests are getting, if P95 is 2 seconds or 3 seconds, it means that out of 100 requests, my 95 requests are getting served in 3 seconds, but rest 5 are not getting. By this is a clear vision or a clear understanding of how as an engineer we can know where the time or which requests are taking more time, or what is the latency of our application. Because if we take average, we won't know clearly which thing is taking, or what is the performance, clear performance of our application. I would call it as average trap, which generally engineer falls in. So instead of taking average, we should try to see other metrics like percentiles and different distributions if possible. We can make different distributions. Then let's not get into mathematics or statistics. Okay, let's conclude our lecture for today. These were the, on the whole, we discussed the high level of how we would create our AI applications. What are the things we should think before the application is, before we start creating the application, and what are the evaluation mechanisms, and of what or which model should we choose, how should we optimize models for our costs, and whether we should fine tune or not to fine tune. And we have discussed a high level view of distillation and LoRa and those things I just told you. We will have a deep dive in of this in future. And we have discussed different latency measure for AI applications like TTP, TTFT, TPS, and different types of TPS like PTPS, perceived tokens per second, and total TPS, TTPS, and ITL, etc. Inter-token limitation, inter-token latency, these kind of things we discussed. I hope this lecture was not too heavy and just an introduction of how you should think as a AI engineer or inference engineer before creating your final application. Thank you.